welcome to my channel. Today I want to show you the complete proof of the Bolzano-Weistrass theorem. Now there are a lot of versions of this theorem, but the main idea is the same. It basically says that a metric space is topologically compact if and only if it is sequentially compact. First, we prove this direction because it is slightly easier. And we will prove this by contradiction. First, we need a lemma. The lemma says if there exists a sequence xn in M that doesn't have a convergent subsequence. Notice here that the condition is the inverse of the statement. If we want to prove by contradiction, then we need to first conjugate the condition. Then for every x that belongs to M, there exists an epsilon x such that this is finite. This basically says that there exists a ball which centers at x and has the radius epsilon x, contains finitely many numbers of the sequence xn. Just like that. And we want to prove this again by contradiction. So let us assume that there exists an x in M such that for every ball that is centered at x contains infinitely many members of the sequence xn. But then we arrive at a contradiction. Let me show you why. Let us assume that the biggest ball here has radius epsilon, and the second ball here has radius epsilon half, and the third ball here has 1/3 of epsilon. We can find here an xn1 because it is a member of xn. We want to find a subsequence of xn. Here we can find another xn2, and here we find xn3, and so on. So we arrive at a subsequence of xn, which is x and k. This sequence converges to x. The limit here, if k goes to infinity, x and k is x. Have you seen the contradiction? You see, we have assumed in the beginning that xn doesn't have a convergent subsequence, but here we have actually found a convergent subsequence, so it is a contradiction. Therefore, our lemma holds. Now, armed with the lemma, we can finally prove the one direction of this theorem. So first, we need to contradict this condition here. We assume that there exists a sequence xn in M such that it does not have a convergent subsequence. And we want to prove that the metric space M is topologically compact. And by topologically compact, I mean for every open cover of M, there exists a finite subcover. Let me draw a line here. And let this line be the metric space M. There are only a finite number of the sequence xm in each open cover. And since the number of open cover is finite, and the number of xn in each open cover is finite, then the sequence xn has to be finite. But you know, the definition of a sequence is that it contains infinitely many numbers, so we cannot call it a sequence, therefore it is a contradiction. So we have now proved one direction of the theorem. Now let's look at the other direction. To prove the other direction, we need the help of two lemmas. Let's look at the first lemma. It says if M is sequentially compact, then for every epsilon there exists a finite number of x1 to xn such that the union of all these balls form an open cover of M. There is nothing very fancy about this lemma, so we are just going to prove it by finding such x1 to xm. Firstly, we find a point x1 here, and let's draw the ball. This ball is centered at x1 and has radius epsilon. And if this ball is just the metric space N, then we have find such an x1. But if it's not, then we continue find the second x, x2. And let me draw a ball here. If these two forms an open cover of M, then we stop. If not, we continue to find the third one. And it goes on and on and on. However, this process must stop after a finite number of steps, because in the end, if we cannot find an open cover to cover this small little gap here, then the sequence we have just found is divergent. Notice here the radius of all these open balls are epsilon. There's always a gap over here, so let's call it x1, xn, and this is xm. Then the distance between xn and xm is always larger than 2 epsilon, which is impossible. Therefore, it is a contradiction to our assumption. This lemma tells us that if big U is an open cover, then for every element of this metric space, we can find a ball that is contained in this open set. So if this X is right here, then we can find a ball that is contained in this open set. It will not, stand across these two open sets. It will always manage to stay inside this open set. And we are going to prove this by contradiction. Let us assume for every epsilon that is larger than 0, there exists an X such that this ball here is not contained in U. For every U that belongs to the open cover U. The epsilon here can be any number. Let us assume that it is equal to 1 over m. And let this X be associated with this m. And here we get a sequence xn. Since m is sequentially compact, we can always find a convergent subsequence x and k of xn. We assume that this subsequence here converges to x. Then there must be an open set that belongs to the open cover here that contains x. Let me draw you a picture. So here is x, and here is the open set. Sorry. Oops. And since this is open, by the definition of open, we can find a ball that is centered at x, which is contained in U. So this ball, let us assume, has radius epsilon. And remember, we have found the sequence that is convergent. So by the definition of convergent, we can find a x and k that is very, 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 very close to x. And we assume the distance between x and k is smaller than epsilon half. And we find this nk to be so large that 1 over nk is also smaller than epsilon half. Now I'm going to tell you that the ball here is contained. This ball here, now I'm going to tell you that this ball here with radius 1 over nk centered at x and k is contained in this U. And if we can prove this, then we have arrived at a contradiction. Because according to our assumption, for every epsilon, in this case epsilon equals 1 over nk, there exists a x and k such that this ball here does not belong to any U, but here it is. See? So if we can prove that this ball is containing U, then we have proved this lemma. Okay, so let me show you how. For every y that is inside this ball here, we can find that the distance between y and xn is smaller than the radius of this ball, so it is smaller than epsilon half. And we can also find the distance between y and x. Y and x is by the property of the metric space, the distance between y and x is smaller or equal to this. This is the triangle inequality. And this here, by our assumption, is smaller than 1 over x and k. And this one, by our assumption, is smaller than half epsilon. And it is smaller than epsilon. Therefore, the distance between these two is smaller than the radius of this ball. Therefore, it is contained. Therefore, the distance between y and x is smaller than the radius of this ball. Therefore, this ball here is contained in this medium ball, and therefore it is containing U. So now we have proved this lemma. Now that we have these two lemmas, we can finally prove the other direction of the theorem. So let us suppose that this is an open cover of the metric space M. Let's call it U. And this U is arbitrary, so we only need to prove that it has a finite subcover. By our previous lemma 2, there exists an epsilon such that for every x, this ball which has radius epsilon is contained in this U. And remember, by our previous lemma 2, all these balls are contained in some U. So for example, if the first one is containing U1, the last one is containing UN, then these open set forms a cover of M, and it is finite. Therefore, M is topologically compact.